Hello everyone, today we're going to talk about the second day of vectors. So this is still section 7.7, but the second half of it. Alright, our first definition has given us a vector V. And remember, these images are all in the PowerPoint accompanying the video. So if this is hard to see, you can go ahead and copy that down from the PowerPoint and then come on back. So my vector V with components A and B can be expressed into terms I and J, basically X and Y, okay? Where V equals AB is now equal to A times I plus B times J, and I'll show you what this looks like. So if we're given the vector U is 5, negative 8, I want it in terms of I and J, where I and J are unit vectors, basically just telling us which is the X, which is the Y component. So all that looks like is U equals 5I minus 8J. Okay, so we're just taking the X, if you want to think A as the X, goes in the first, and 8 as the Y goes in the second with our I and J components. That's all they were asking there, to put it in that form. Once we do that, we can manipulate it like we did in the previous, in the first half of chapter 7, section 7.7. So if we're given U is this with, remember, just think of this as 3I as the X component and 2J as the Y component, and V, negative I, 6J, find 2U plus 5V in terms of I and J. So I want 2U plus 5V. Well, I'm going to first of all take 2 and multiply it by U. And then I'm going to add that to 5 being multiplied by V. Okay, so distribute. And then we can go ahead and just combine like terms like we always have. Just think of it as combining like terms. So the result of 2U plus 5V, I'm going to have 6I. So they like to do 6 minus 5, and that's all being multiplied by I, plus 4 and 30J. So my overall resultant force is just going to be 1I plus 34J. Right? And just like everything else, you don't need to write the 1. So you can just say I plus 34J. That's the resultant force when we take 2U plus 5V. Next, we are told that a vector with a magnitude, and we already covered magnitude, right? Basically the distance, okay? And direction theta. Then our vector V can be in terms of IA, remember just the X component, Y component, where A is the magnitude of V, so the distance, okay, times cosine theta, and B is the magnitude of V times sine theta, again, our X, Y components, okay. So they tell us the vector V has length 8 and direction pi over 3. They want us to find the horizontal and vertical components and then write them in terms of I and J. So, again, our A, okay, remember, just think of A as your X component, right? It's the horizontal component. A is equal to the magnitude of V, okay? They're telling us it's length 8, so that's the magnitude. Cosine, pi over 3. Pi over 3 is, if you want to think about it, is the direction, right? So my angle, so I've gone length 8 at pi over 3, okay? And that gives me 8 times 1/2. So our unit circle hasn't gone away yet. We have to remember cosine pi over 3 is 1/2. Okay, so my X component is just 4. My Y component B, okay, is 8. Right? So my magnitude, my distance, sine pi over 3. And again, we should know that that's 8 times radical 3 over 2. Okay, so that Y component is 4 radical 3. So x component, if you want to think of it like that, my a, 4, y component, or my b, 4 radical 3. I want to write v in terms of I and j. So my vector v is really 4i, my x component, plus 4 radical 3 j, my y component. Next part of the problem asks us to find the direction of vector u given the horizontal and the vertical component. So we can go ahead and use our definition up above. So the first thing we're going to need to do is I would draw the vector so you can kind of see what you're looking at. So just a brief sketch. Okay, so we can see that our x component is negative radical 3. Okay, so negative radical 3. Something like that, right? That distance there. And our y component is just 1. So we'll call that 1. So our actual vector v is something like that. Okay, where we have y component 1, x component negative radical 3. Okay, so that's really what we're looking for. We want the direction. We want to know the angle of v. Okay, so to do that, we're basically looking for theta. And what we got to think of theta, theta is just like slope, rise over run. Okay, so we're going to use tangent because tangent is rise over run, right? It's your y value over your x value. Okay, so we know our y value is 1. We know our x value is negative radical 3. Well, I want to know theta. So remember, whenever we're looking for an angle, we do the inverse tangent. Okay, and if we do that, you can have this in degree mode. Probably better to have it in degree mode, right? Because radian is going to give us a decimal. We're not going to understand what it means. But in degree mode, if you were to do this, you get negative 30 degrees. Well, negative 30 degrees doesn't make a whole lot of sense to us, right? Because we're not in the fourth quadrant. We're actually in the second quadrant. But that makes sense because tangent is negative in the second quadrant, if we remember. So they're really giving us the reference number of the second quadrant, meaning that our theta is actually 150 degrees. Okay, so theta, 150 degrees, or if we want it in radians, it'll be 5 pi over 6. So it depends what they're asking for. Either one of those answers I would take. Next question. We have an airplane heading due north at 300 miles per hour. It experiences a 40 mile per hour crosswind in the direction 30 degrees northeast. So what that means, that 30 degrees northeast means instead of being straight north, it's 30 degrees east off of north. Okay, so that's how they do their heading, right? So they start, instead of starting on the x-axis and giving me my angle from there, they start at the y-axis and say it's 30 degrees east of north. Okay, so that's really what this crosswind is doing. So the first part asks us to express the velocity v of the plane relative to the air and the velocity u of the wind, and they just want them in component form like we did in the previous examples. So we're basically just taking our previous examples now and we're putting it into real world situations. So v is pretty easy because it's going straight north, right? It has a 0 x coordinate. We haven't gone left or right. So it's just 0i plus 300 j, right? Because it's going due north at 300 miles per hour. So it has a y component of 300. So the resultant force of v is just 300 j, strictly 300 degrees in the y value. U, we're going to have to use our definition from the previous one, that we have a magnitude of 40, okay, and then cosine, because we have an angle of 30 degrees. So when we, remember, our trig functions actually use how far the angle is away from the x-axis. So this takes a little bit of thinking here, a little intuition to realize that, okay, if I were to draw this angle, right, it's in the first quadrant because it's 30 degrees. It's 30 degrees east of north, right? It's 30 degrees off of there. Remember, our trig functions, and this takes a little bit of thinking, they want to know how far it is away from the x-axis. Okay, so that takes a little bit of thinking to realize I don't plug 30 in here. I actually plug 60 in for my theta, right? Because theta is measured in how far away from the x-axis. So you really got to understand that. So that just means I take cosine of 60 degrees plus, and then I also want the, and that's 40 times cosine 60 degrees I, right? Because that's the I component, plus 40 sine 60 J. Okay, so that's your Y component. So as I work this down, I get 40, and cosine of 60 degrees is 1/2. Again, our unit circle hasn't gone anywhere, and that's our I component. And plus 40 sine of 60 is radical 3/2. That's our J component. So, final answer, U is 20I. Okay, so that's your X component, 20 units up, or I'm sorry, 20 units across. And then our J, we're allowed to approximate this because we're actually going to graph these. So you can actually type this into your calculator. It doesn't have to be exact. And in fact, you don't want it to be exact because you don't know exactly where radical 3 will put us. So it's approximately 34.64 J. Okay, so the wind has 20 degrees, or I'm sorry, a 20 X value and a 34 Y value. That's what's actually acting on the airplane that wants to go due north. Okay? So if I have an airplane that wants to go due north, but I have a crosswind that's acting with this magnitude here, I want to find the true velocity of the airplane, right? After vector W, I'm calling it W because it's the wind is acting on the airplane. So what that really leads us to do is the wind is going to be my vector V, the plane, plus my vector U, that crosswind that's affecting the plane. So all I do is take my vector V, which is just 300J, right? It only has a Y component, if we remember back up. Add that to my 20I, plus 34.64J, right? That comes from our components that we found for U. So my overall effect is I don't have any X component in the V, so that's just 20I, and then plus 334.64J, right? I'm just adding the two J components. Think of it as combining like terms. So that is actually the true velocity of the airplane as a vector W. Final thing that we need to answer is, well, this is good and this is all good and well, but what's the actual speed of the airplane now? And the direction, where are we going? So the airplane wants to go directly 300 miles an hour north, but it's getting a crosswind going 30 degrees east of north, remember. So I want to know exactly where is my airplane going to be going, given that crosswind affecting it. So we know how to find the magnitude. That's from the first part of 7.7. So the magnitude of W, right, because the W was our overall wind effect, and that's equal to the square root of 20 squared, just your X component, plus 334.64 squared. So how fast is that airplane going? It's going 335.2 miles per hour, right? Because that crosswind is actually helping it go faster than the 300 miles per hour it was going directly north. But which direction is it going? Okay, so remember direction we just solved for? Tan theta, because it's rise over run, and our y value is 334.64. Our x value is 20. So my theta is 86.6 degrees. Now, remember, that theta is how far off the x-axis we are, right? Because that's how our thetas work. Heading is how far off the y-axis we are. So we actually have to do a little thinking here to figure out the magnitude and vector. So I'm going to give you just a rough sketch, right, of what's happening here. So if we had any point P, right, and we got 300 miles per hour V, that crosswind U, okay, that we found, and they said that's actually 40 miles per hour, so something like that, and it's at a 30-degree angle. My overall W is now going to be at 86.6 degrees, okay, so almost 90, but it's at 334.64 miles per hour. So that's what's really happening to our airplane. It's going 300 miles per hour directly north. It has this crosswind. The net effect W puts it at about this angle here at this speed. Now remember, that means my heading, well, let me just write it out. So the speed, okay, is 335.2 miles per hour. Okay, but my heading is not 86.6, because remember, the heading is how far off of north we are. So it's really only north 3.4 degrees east. Right? It's only 3.4 degrees off of being directly north. Final example. We have two forces, F1 and F2, with a magnitude of 10. Okay, so my magnitude of 10, and that's obviously this one right here, the smaller magnitude of 10, and 20 for F2. Act on an object at point P, okay, so wherever point P happens to be. Find the resultant force acting at P. So basically I have one force pulling in this direction at 45 degrees. I have the other force pulling in this direction at 150 degrees, with obviously F2 being a stronger force. I want to know where I'm going to end up being. Like, where is this actually going to pull me? Okay? And just intuitively I can think, okay, it's definitely going to go more towards F2, right? Because it has a stronger force pulling on it. So, first thing I'm going to have to do is find F1 and F2 in component form. Okay, so they didn't explicitly tell us this, but that's the first thing we're going to have to do is find F1 in component form to actually know, okay, how strong is this force? So I just take 10, because that's the magnitude, right? That's how hard it's pulling. 10 cosine 45, because that's the angle that it's given us. And that is our I component. And we have 10 sine 45, because that's our J component. So overall, I get 10 cosine 45 is radical 2 over 2. You still have to know it. That's our I. 10 sine 45 is still radical 2 over 2. That's our J. So our F component is going to be 5 radical 2 I plus 5 radical 2J. So that is this force here, this F1. Now F2, we do the same process. Okay, except it's going to be 20 cosine 150 degrees is our I component, and 20 sine 150 degrees is our J component. Okay, so we simplify this. That's going to be 20 negative radical 3 over 2 I. Because remember, cosine of 150 degrees is going to be negative. Our x values are negative at 150 degrees. Plus 20, and then this is just going to be 1/2 J. So this is why I stress the unit circle over and over. It'll help you so much if you can just remember how to find sine 150 and cosine 150. It'll make your life a whole lot easier doing these magnitudes, these forces. Okay, so that gives us negative 10 radical 3I plus just 10J. So the x and y components of that force F2. Once we have found those two components, these forces, then we can go ahead and figure out the resultant force, right? So where is this vector going to be after those two vectors are being acted on it? So I take F1 plus F2, okay, and we know F1 is 5 radical 2, and that's 5 radical 2I plus 5 radical 2J. And we're going to add that to F2, which we just found is negative 10 radical 3I plus 10J. Now again, just combine like terms. So we get 5 radical 2 minus 10 radical 3, and all of that is our I. And then we're going to add that to our 5 radical 2 plus 10, and all of that is our J, right? I've just combined like terms. So that gives me a resultant force. And remember, we don't care about exact right now because we're actually going to plot these. So that gives me a resultant force of about negative 10.25 I. That's our x component. And 17.07 J. That's our y component. Now they didn't ask you to graph it, but I'm going to visually show you what's happening here. And remember, this can be any point P. I'm just going to do it at the origin because that's how our brains work. Like, it hasn't been translated, right? So I'm just going to do it at the origin to show you exactly how this worked. So we had our F1. So our F1 was at, it had a 5 radical 2 for your x and a 5 radical 2 for your y with a 45 degree angle. So 5 radical 2 is about 7.1, so just a little bit more than 7, and then a little bit more than 7. So something like that. Okay, so that was F1. Okay, that's with the 45 degree angle, but that has 7.1, 7.1 as your x and y components. That's what we actually solved for. So I can actually graph this pretty accurately. F2 had an x component of negative 10 radical 3, which actually turns out to be negative 17.32. So negative 17.32. And it had a y component of positive 10. Let me make sure. 1, 2. Yeah, actually, I have to go up one more. Okay, and that is my F2, which remember had 150 degrees for the heading. So my resultant force F that I just solved for, if we look back, had an x component of negative 10.25 and a y component of 17.07. So negative 10.25 and then 17, basically 0.1. Something like that. Let me make sure. Okay, so 10.25, 17.1. I'm sorry, that's not F2. That is just my final force F. That's actually where that object is going to be pulled with these two forces acting on it. Okay, so go ahead and try those examples in the PowerPoint and try the practice problems that accompany it as well.